Thank you very much. Thank you all for joining my talk, and thanks to the organizers for setting up this beautiful conference and for giving me the opportunity to talk here today. So this is joint work with Elie de Panafieux from France. So let me start with the motivation why we started to study such walks, and I'll define everything afterwards. So everything here arose from a problem in networking, where basically what you're interested in, you have like a big network and you want to send a message over that network. So this is a scheme as sketched up here. So you have some message you want to send, and then basically the routers which send then the message over this network, they use different protocols, and because of this, you have to encapsulate your data in order to transmit it. And this is here sketched by an E. So in the beginning, there is like a message sent, it's encapsulated, it's put into like a ball here, this blue ball, and then it's continued. And then it might be encapsulated twice. So we have like two balls, then it's decapsulated, which is denoted by this D. So we take one shell away and so on. And the question is now, is it possible to find a path through my network such that at the very end, I have the message without any overhead anymore? So basically all that can be mimicked, or this topology here, when we assign to these routers, to these nodes, these capabilities of encapsulating or decapsulating, what we need to track is like the number of encapsulation or decapsulation steps. And basically that can be modeled by a classical dig path, where encapsulation is an up step and decapsulation is a down step. And the height is then nothing else than the number of shells you have around your message. So basically here we have EE, which corresponds to two up steps. Then we have a D for decapsulation. We have a down step, an up, a down, and a down. But of course, here in this topology, this is pretty simple. And if these routers are just capable of doing that, that's a bit boring. So obviously, most of the times, they can do both. They can encapsulate or decapsulate. And basically here, I sketched this by these red nodes, encapsulation and decapsulation steps. And then there's a choice what they want to do. The idea is that at the very end, you want to get your message back. And this can be modeled again by paths, by a generalization of paths, which we call non-deterministic dig paths. So in the classical dig paths, we have steps +1, -1 in this case, for dig paths. And in non-deterministic paths, you have sets of steps. So your steps are sets. So they could be singletons, like -1, 1, or they could be two element steps, like the -1, 1 step. And this red step corresponds to this encapsulation decapsulation event. So you have a choice, and what you do, you simultaneously follow both paths. So basically you follow two trajectories simultaneously. So here you have a path, it's a sequence of steps. So you then up, you have this special fork which goes up and down at the same time. Then you have a down which goes down on both of these trajectories, up again, and then you have another fork which forks on all possibilities. And basically you're then interested in these topologies, in these paths, which basically mimic, which are in bijection, with the topologies you had on the top. And the question in networking people were interested in is it possible to find like a path through this trajectory such that I can come back to the message at the very end? In terms of paths, this means that you have a path which stays above the x-axis and comes back like this path here. Okay, so far for the motivation. We are interested in four different types of walks. And they are classical notions for classical walks. So I call a walk a completely unconstrained sequence of steps. And this I call an N walk, basically, meaning it's defined by the fact that it contains a walk. So you see on the bottom left an N walk. And in red, you see one walk, but there's other walks there as well. Then a bridge I call classically a walk that ends at 0 again. So you see one in red here. This is a classical bridge in turn we're using dig paths, dig steps. And the N bridge, the non-deterministic bridge, is an N walk that contains a bridge. So you see here that at this step it forks basically into two trajectories, but we don't care so much. At the very end, there's like one bridge in here, at least one. There could be multiple ones, but I call it an N bridge if it contains at least one bridge. So you always have to think of the non-deterministic walk as the all possible trajectories. And we call it an N bridge if there's one trajectory in there that's actually satisfies my properties here returning to 0. A meander is now an object, a path that stays non-negative, so never goes below the x-axis. So here in red you see one, so it goes up, 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 then never goes below the x-axis. It could touch it, this one doesn't, but it doesn't matter. And an N meander is now an N walk that contains a meander, but the n meander is this full object. And an excursion is a path that is simultaneously a bridge and a meander, meaning it stays non-negative and it ends at 0. And you see here an n excursion is then nothing else than basically an n walk that contains at least one excursion, which you see here. It could have different trajectories which you think of excursions, but basically these is the ones. And we are interested in these ones. Each of these paths of these non-deterministic walks corresponds to one such topology on the network, and we're interested in certain of them. But the first step we want to do here, we want to count these objects in order to analyze them further. So the key notion here to study these is like to understand their ending points. And their ending points in classical paths, it's just one thing. You just continue where it just ended and continue with the allowed steps. But here you have several points, several reachable points. And these is the ones we need to understand. And here we use a classical notion from additive combinatorics, the Minkowski sum. So if you have two sets, A and B, the Minkowski sum is defined as the sum of all possibilities from these two sets. So now let me give you a rigorous definition of the n walks. And this is like really, don't come back to the network motivation. Here I stay from now on my walk interpretation. So I call an n step set a subset of the power set that is finite. So for dig n walks, this is the step set -1, the singleton 1, and the two element set -1, 1. And on the left here, you see an example of one of these trajectories. And an n walk is nothing else than a sequence of certain steps. So here you have the sequence -1, -1, 1, -1, 1. So then the reachable points are now nothing else than the sequence of my allowed steps, of my used steps, basically, the Minkowski sum of these. So in this case, we do a -1, then this is this down step, then we do a -1, 1. So we simultaneously go up and down. And then we do another -1, 1, this fork, and we do simultaneously a 1 and up and down on all of them. And so my reachable points are then nothing else than this Minkowski sum. So this is the -3 here, the -1, and the 1. And what I need to understand here is two parameters, the minimum, which I denote by min w, which is a -3, and the maximum, which is here 1 in this case. And we're going to use generating function in order to understand these objects. So I defined the trivariate generating function dxyt, where I need x and y as catalytic variables in order to model them. So they capture the reachable points. So in x, it's the minimum of the reachable points. In y, it's the maximum of the reachable points. And in t, I capture the length. And now it's just very classical you just apply standard symbolic computations for generating functions. It's just a sequence. It stays a sequence. It's a sequence of these steps. So we track each step with a t variable for the length, and then we have a down and up and a fork. And what we need to take care of now is the change in the min and the max of the reachable points. And basically, this will be my most complicated proof just to convince you that you can work with these objects. So basically here, we just need to track that the down, what is it doing to the min and the max? Well, it decreases both. So we need to decrease the min and the max. So the up then increases both, and the fork in this case, it decreases the min and it increases the max. So basically we got here the full generating function. And if we want to know the total number, of course, we could just sub in 1, 1 for x and y, but obviously here it's super clear that it's just a sequence. There's 3 to the n dig walks of length n, that's clear. And in general, it will be cardinality to the number of steps, obviously. Okay, so this is for starters. And now we're going to look at the other walks in more detail. So let me start with dig n bridges. So let me remind you that the step set is the singleton 1, the singleton -1, and the two element set -1, 1. So an n bridge is an n walk containing that. So it could end like that with a final up jump. It could end like that with a final down, or it could end with a fork. This is the possibilities. And what you can get, if you think a little bit of that, of course, an n bridge has to have even length. That's pretty obvious because at odd lengths, they cannot reach the x-axis again. And the minimum has to be less than or equal to 0 and the max bigger than or equal to 0. And that's actually already characterization. And from that, you get like the theorem for dig n bridges. So they are algebraic of degree 4. And their generating function is for the total number where we don't care for min and max is given by this nice expression, completely explicit, meaning we have, of course, we have 7 paths, dig n bridges of length 2 and so on. But what was surprising for us here in this was that if I look at the asymptotics, the asymptotics behaves like 3 to the 2n minus some exponential corrections which are smaller than the 9 here, so the 3 squared, and polynomial corrections. But if you recall, the total number of these paths is 3 to the length, so 3 to the 2n. But that basically tells you that in these dig and bridges, if you take a random dig and walk, it will be with probability 1 a dig and bridge if you go to infinity, and length goes to infinity. And that's completely a different behavior than for normal classical paths. Okay, so let's look at meanders. So for meanders, we again look at the dig step set, -1, 1, and the fork. And now a meander is like one of these constructions that has at least one meander in it. So basically we stay non-negative. So here the dashed lines tell you that we don't care for these trajectories because they are not meanders. They cannot help us anymore. Only these ones, we need to continue these ones because these ones are basically dead for us. Here we redefine basically the Minkowski sum to stay non-negative. Again, the same generating function. I did not here apply plus the fact that they can never be negative. And again, we can prove that the generating function is algebraic of degree 4, and it's completely explicit. The idea here is, and here I can nicely connect to Doron's talk, basically that it's the kernel method, which Doron doesn't like so much, but here it was really, really helpful. And what you can get here, the asymptotics of n meanders, which is this one. And here again, the asymptotic growth is 3 to the n over 2, and corrections which are smaller exponential order. Meaning, this means that if you take uniformly at random a large dig and walk, with probability 1/2, it will be a dig and meander. And for dig and excursions, which you get when you sub in 0, 1, then we have basically here this correction is for even, so you have even length, that's obvious, again, like for bridges, and you have the asymptotics 3n over 4, and these corrections here, which are smaller in exponential growth. But here it means 1 over 4, meaning the probability of a random dig and walk to be a dig and excursion is 1 over 4. And that's completely different behavior than for classical ones. Okay, so a quick application to networking, because people were actually interested in, we sample uniformly at random a topology, and they wanted to have a topology to test algorithms that has an excursion in there, that has a path so that the message can be encapsulated. And for that, we assign weights -1 for the -1 jump, decapsulation, 1 for the up jumps, encapsulation, or for the fork, -1, 1. And what you get, and let me just briefly tell you, because I don't want to go over time too much, basically, we can completely make explicit these probabilities and then tune the samplers. Here you see the theoretical results, and there's 3 different behaviors depending if these probabilities are less than 1/2. If one of them is equal to 1/2, then you have a behavior like square root of n. If you have both of them 1/2, this is the classical dig paths. So you have the behavior which we all know for n to the -3 over 2. And if one of them is less than 1/2 and one of them is bigger than 1/2, then you have an exponential decay and a polynomial correction. And this is these 3 terms which you see here. But this was one motivation to do this. And an obvious question is other n steps. This was dig n steps. So for Motzkin n steps, we called Motzkin n steps all subsets of the Motzkin steps, where you have an up step, a level step, a 0 step, and a 1 step. And so the step set for Motzkin n steps, we call this one. We have these 3 singletons, 3 2-element sets, and this big one, which has all of them. And again, what we can see, all of these classes, Motzkin n bridges, n meanders, and n excursions are algebraic. Here you see an example. Here it still worked very nicely. But for general n steps, it's much more complicated. So we could prove, and this was quite involved, that for general steps, you can choose any n step you want. The generating function of bridges in 3 variables, x, y, t, where x is the min of the reachable points and y is the max of the reachable points, is always algebraic. That was quite involved. But for n meanders, we just have partial results. We have results that certain n meanders, non-deterministic meanders, are algebraic. For example, the ones 0, 0, which end with the min and the max both at 0. But we couldn't prove, but we conjectured the algebraicity of n excursions. So n meanders they are, because you wouldn't just do sub in y equals to 1. That's fine, that's easy. But the algebraicity of n excursions, which is the interesting fact, we couldn't prove. We're quite optimistic that it's true, but we cannot prove it. Okay, So this brings me to the end. So basically, we considered actually here just one simple topology, just the line graph. So of course, it would be interesting to look at other topologies. We have just one protocol in this case, and this was already complicated. Of course, a natural extension is more protocols, which people in networking are interesting. You see an example here with two protocols. One is blue, one is red, and then you also allowed like continuing without encapsulation or decapsulation. And a deeper question is to understand everything. A lot of these objects were algebraic. And this kind of suggests that there is some context-free grammars behind these paths. It's obvious that there should be some, but to find explicit one and to understand them is quite an interesting and intriguing question. So that's it. Thank you very much for listening, and I'm happy to answer your questions.